Alright, in this video I'm going to be going over ways to interpret the derivative in the context of specific problems. So the first thing I'd like to go over is an example that we sort of already discussed, which is if d of t is equal to the position of an object on the x-axis. And let's say that we're given that this is measured in meters, and this is at time t measured in, let's say, seconds. So we've already said that represents the instantaneous velocity of this object at time t, and we have a definition for that. D prime of t is equal to the limit as h goes to 0 d of t plus h minus d of t divided by h. And so what I'd like to point out here is that in the numerator we only have things relating to d of t. So the units in the numerator are the same as the units of d, which are meters, and the units in the denominator are the same as the units of t, because remember that where this h comes from was really t plus h minus t, so a difference of 2 times, which gives us h. So the units here are seconds. So that means when we have this quotient here, the units for the numerator are meters, the units for the denominator are seconds, so the units for this entire thing are meters per second, and adding in the limit as h goes to 0 doesn't change that. So the units for the derivative are meters per second. And these are the typical units for velocity, so this makes sense with what we think the derivative should mean. And so what does instantaneous velocity really tell us then? So if d prime of, let's say, 2 is equal to 45 meters per second, this is saying that if the object continued to travel at the same rate as it was at the start of the second, then it would travel an additional 45 meters in the next second. However, the velocity could change during that second, so the actual position at time 3 seconds may not be 45 meters higher than what it was at time 2. So, for example, let's say d of 2 is equal to 10. Then what the graph might look like is something like the following. So this is t, this is d of t, and let's say this is 2, this is 3. So d prime of 2 gives us the slope of the tangent line at 2. So that will be the slope of this line. And so this is predicting that at time 3, the object will be here, which would be, if this is 10, this predicted height from the tangent line would be 10 plus 45, which is 55. However, the actual value of the function is somewhere up here. So this tells us that the object was actually increasing its speed between t equals 2 and t equals 3 because the function is going up steeper than the tangent line at 2. So this is an example where because the slope is changing, the position of the object is not the same as if it was just to continue going at that same speed as it was at the start of t equals 2, at the start of the second. So really, when you write something about the interpretation of what the derivative means, you really have to take into account that it's at that moment, this is what the speed is, but when we move away from that moment, the speed can change. So let's see another example in a slightly different context. So let's define g of t equals the average price of gas in the US at the start of the year 2000. So on January 1st, 2000. So first let's think about what the units for g prime are. Well, based on this example here, how do we figure out the units? It's the units for the numerator in this difference quotient divided by the units in the denominator. And so the units in the numerator will be the units for the output variable, which is g in this case. And so the price will be measured in dollars. So that means the units in the numerator for g prime should be dollars. The units in the denominator will be the units for the input variable, which in this case is time. And we're measuring time, I guess I didn't say, but t is in years since the start of 2000. So this would be dollars per year are the units for g prime. And so if we were told something like, let's say g of 2 is equal to $2.50, and let's say g prime of 2 is equal to 0.5 cents, then what is this information telling us? It's saying that at the start of the year 2002, the gas price was going up at a rate of $0.5 per year. And so, based on the value that we were given, g of 2 equals 2.5, we can predict that g of 3 will be approximately equal to the value at the start of year 2 plus the rate at which it was increasing, which was g prime of 2, times the length of time it was increasing for, which was 1 year, so times 1. So this would give us $3. So we could predict the price of gas at the start of the next year using the derivative at the start of year 2, or 2002. But we have to keep in mind, just like in this example, that the rate at which the gas price is changing might also be changing over the course of that year, so that the actual gas price may not be $3. So it's important to say that this is an approximation to g of 3 using the information that we have. And we'll see this is what's known as a linear approximation. And we will revisit that idea later in the class. But I think the main thing for now to keep in mind is that what the derivative is telling you is it's the rate of change at that moment. And you can figure out how to sort of interpret that in context using the units for the derivative. It's telling you that the output variable, in this case dollars, is going up by this amount each year at the start of year 2002.